Good morning, students. I, Jeevan Kumar Pandey, welcome you once again to the next session of our discussions in first chapter of electrostatics in physics. So far we have discussed about Coulomb's law. We have seen some problems, numericals. The next topic that we would like to start today is electric field, before which a small subtopic I would like to discuss about dielectric constant. Since we have already seen that the Coulomb's law says that the force between a pair of charges is given by the formula 1 upon 4 pi epsilon naught, the product of charges q1 q2 divided by square of distance between them. But this formula we have discussed in vacuum. That means when there is no medium separating these two charges q1 and q2. What would happen if I put these two charges in some medium? For example, oil, water, glass, etc. In presence of medium, we find that the force between the pair of charges gets changed. The force in a medium would be given by the formula Fm 1 upon 4 pi epsilon naught multiplied by another constant which we write as epsilon r. Rest parameters remain same, like so. See carefully the difference between these two formulae. This quantity epsilon r is called as dielectric constant of the medium. The more is the dielectric constant of a medium, the lesser will be the force between the pair of charges. Now you can see, you can divide these two relations. We can find the ratio F by Fm. Force between a pair of charges in vacuum divided by force between same pair of charges separated by same distance but in presence of a medium. So F by Fm will become equal to, you can see this by this. So many factors, 1 by 4 pi epsilon naught will cancel, q1 q2 will also cancel, r square will also cancel. The only thing that remains will be epsilon r. So this gives you the defining equation for epsilon r. How do we define it? The dielectric constant of a medium is defined as the ratio of force between pair of charges in vacuum to force between same pair of charges separated by same distance in that medium. The value of epsilon r for some dielectrics you can find in the textbook. For example, in water, for water, epsilon r value is nearly 80. That means this ratio of force between a pair of charges in vacuum to the same pair of charges in water, W for water, epsilon r definition is F by Fm. F by, instead of medium m, I am writing water, that is 80. What does that mean? That means that force between the pair of charges in water will be nearly 1 by 80 times the force in vacuum. Now what is its physical significance? Its physical significance is that one example I would like to cite. You know about common salt. It is Na plus Cl minus. In solid state, the forces between them are quite strong, which bind them quite close to one another. But when we add a pinch of salt into water, what happens Now between these Na plus and Cl minus ion, the medium is no longer vacuum, it is rather water. So therefore the force between these two oppositely charged ions gets reduced by a factor of 80. That is a very large value. That means the electrostatic force of attraction between these two gets reduced by 80 times when the salt is immersed in water. And that once the force is reduced, they can easily be separated. So Na plus and Cl minus, after providing a little bit of energy, will get easily separated and they will mix easily in the water, resulting in dissolution of salt. So this is the meaning of dielectric constant, students. Next, we would like to switch over to electric field. The concept of electric field is very important. Coulomb's law we have discussed, students, that if there is a charge, say Q, and we have another point charge, say small q, then it exerts a force. This force, remember students, is not instantaneous. What do I mean by that? Suppose we have only charge q in space, there is no other charge. Now we bring a small charge, small q, and put at some distance from this charge. Let that distance be small r. What I mean when I say the force is not instantaneous, if I bring this charge q at time t is equal to 0, when I place this charge at this point, it is t is equal to 0. It will experience force due to this charge after a time t which will be equal to r by c. Now this is very important. And here comes the concept of field. This charge does not experience the force instantly when it is placed over here. Rather, it is a two-step process. This charge capital Q, in its vicinity, in its neighborhood, in its 3D space surrounding it, it first creates a region which we call as field, electric field. In that electric field, when another charge q is placed, that charge q experiences some force. And this field is not an imaginary quantity. In fact, in physics, we take it as a physical quantity, just as you take length, mass, time, etc. It is taken as a physical quantity. It has very much existence. This field is electromagnetic in nature and it travels with a speed c away from the charge. If this distance is r, the time that this field takes to reach from this capital Q to this small test charge q will be how much? Speed is distance by time, time will be distance by speed, that is r by c. It takes some time for the charge to experience the force. One rectification I will do here, t is equal to 0 is the time at which this charge is brought. This is already present. I should rectify myself. This charge is present. We bring now a charge capital Q. When we bring charge capital Q, it creates a field. That field travels with a speed c and it takes some time to reach this particular charge. That time is how much? As I told, r by c. After that time only this charge will experience a force. And what will be the value of that force? You know Coulomb's law, F is equal to 1 by 4 pi epsilon naught Q1 Q2 by r square. So this is the meaning of the statement when I say the Coulombic force between two charges is not instantaneous. This field which is generated around the charge, we call it as electric field and we denote it as E vector. It is a vector quantity. On this charge Q, let the force be F vector. It may be attractive, it may be repulsive, depending upon the signs. The test charge that we bring, generally we take it as positive. If this charge Q experiences a force F, then the electric field will define as force per unit charge. Now that gives the definition for electric field. Now here I discussed for one charge. In fact, this definition holds true for any configuration of charges. For example, if we have a system of charges having different point charges q1, q2, q3 and so on, qi, and we bring a test charge which is very small. We bring a small test charge which we write as q, and this test charge is positive. This is a positive test charge. Then this entire system, from principle of superposition, we can find the net force on this. Suppose the net force on this charge particle be like so, and that we write as F. Then the electric field at the location of this point, that electric field will be given as the force experienced per unit charge. Now here one thing I would like to add. Suppose we bring this charge q, and this q is not small, it has a significant value. Then it's not that only these charges will exert force on this. Newton's third law says this will also exert force on the configuration. We wish to find electric field at this point due to this configuration, but the moment we bring this charge, it will attract or repel some of the charges, so their positions might change a bit because of the forces. So therefore the electric field which you will get here will be not due to original configuration but due to the disturbed contribution. Therefore, to minimize this disturbance, what can be done? This test charge which we are bringing must be very small. Therefore, I will make it as small as possible. How small? As small. So we write it in the form limit q tends to 0. So how do we read this? Electric field E vector is equal to limit q tends to 0 F upon q. This is the definition for electric field. Now you can guess the unit for electric field. Force SI unit is Newton, charge SI unit is Coulomb. So the SI unit for electric field will be Newtons per Coulomb. It also has another unit that we will take up in the next chapter, volt per meter. Just to remember this, Newton per Coulomb or volt per meter. Okay, let us try to find the electric field value for a point charge capital Q at some distance. Wherever we wish to find the electric field at this point, which is at a distance r, at that point we will bring a test charge Q. What is small q? It is a small test charge which is positive. We don't bring negative test charge. Of course you can bring, in principle there is no problem, just for the sake of definition. Now this charge may be positive or negative. If it is positive, then it will repel this one, and if it is negative, it will attract that one. We assume both of them to be positive, then the figure will show force like this. This will experience a force, and you know that force will be given by the formula F vector is equal to 1 by 4 pi epsilon naught. If you assume this is medium, then you should put epsilon r. I am taking it as vacuum itself. Product of charges q into q divided by square of distance between them. Now if this is the force between these two charges, then how do we find electric field at this point? We have already discussed, students. The electric field at that location will be force on a charge divided by the charge itself. That means force experienced per unit charge. If you divide F by Q, so let me rectify one more thing. Here I have written a vector. Here I have written its value. I forgot to mention the direction. I must keep the direction. I will choose this vector as R vector. And in this direction, the unit vector I will choose as R cap or R hat. Then I should put here the direction as R hat. So E is F by Q. F by Q, when we will find, this Q will cancel. What will be left is this. 1 upon 4 pi epsilon naught the charge divided by r square times r cap. So this is the electric field due to a point charge. Knowing this value, for a given configuration, we can find the electric field just by using the principle of superposition. Let's see. As you can see, here I have a configuration of charges Q1, Q2, Q3, Q4 up till Qn. This is the ith charge Qi. We wish to find the electric field due to this configuration at some point, say P. Now the position vector of P from different charges are R1 vector from Q1, R2 vector likewise from Q2 and so on, Ri vector from Qi and Rn vector from Qn. So the net electric field at point P will be given from principle of superposition. Just find the electric field due to individual charges and add them using vector laws. So I'll write it as E1 vector plus E2 vector plus E3 vector and so on plus En vector, which I can write as summation Ei vector, where I runs from 1 to n. Now Ei vector, how do we write? Ei vector will become equal to how much? 1 upon 4 pi epsilon naught. Electric field formula is Q upon R square. Ei is the electric field due to this charge Qi. So I'll write Qi upon this distance is Ri. So I'll write Ri square and then vector, unit vector Ri cap. So this is the value of Ei vector, its summation, where I will run from 1 to n. In this way, we will find the net electric field due to a given system of charges. Let us try to solve a question based on electric field. Here you see there are two figures. First we will discuss this one, first question. Here we see there are two charges. One is has a magnitude 2q, other has a magnitude minus q. You have to locate points on the line joining these two charges where the net electric field is 0. Now electric field, I told you, it is the force experienced per unit charge. So what we do basically, we bring a test charge positively charged, we find the force, we divide by that charge, and electric field formula we have already discussed. Before discussing this, let me remind you, if we have a positive charge, then at a point the electric field will be directed away from it. Why? As I told, when you bring a test charge which is positive, always test charge is taken as positive, then it will be repelled. And if we have a negative charge, then at a point the electric field will be towards it, because if we bring a test charge, then the test charge will be attracted. So the direction of electric field is always away from positive charge and towards negative charge. Keeping that in mind, now first you see this charge configuration which is given, I can divide it into three parts. This is region 1, this is region 2 and this is region 3. Is it possible that electric field will be 0 at some point in region 2? Because why we have to think about the regions? First you have to decide, then only we can solve it. If you take a point over here and you put a test charge over here, then or directly you can think the electric field due to this negative charge will be towards it, and electric field at this point due to this one, this is positive, so it will be away from it. So both these vectors will be in same direction, so they cannot cancel. We want net electric field 0, so this region 2 it's not possible to have 0 electric field. So the remaining options are region 1 and 2, region 1 and 3. In region 1, if there is a point like so, due to this minus q charge, electric field will be in this direction towards it. I will write it as E minus vector, and due to this charge, because it is positively charged at this point, its electric field should be directed away from it. So I will write it as E d2 plus 2q vector. This is E d2 minus q, this is E d2 plus 2q. Yes, there is a possibility they can cancel each other. Likewise, here this will have electric field in this direction, E plus 2q, and the negative charge minus q will have electric field in this direction. Here also they are in opposite sign, but the thing is that all those points which we take to the right of this 2q, all these points in the region 3, those points are closer to 2q charge. Out of these two, the magnitude of this charge is double of this. So since this magnitude is double and the distance is also less, force is proportional to the product of charges q1, q2 and inversely proportional to square. If charge is more, the force will be more. And here for this point, for this point, the distance from charge to q is less. If r is less, again force will be more. Therefore, for all these points, the electric field due to plus 2q charge will always be greater compared to the minus q charge electric field. And since it is always greater, it will never cancel. There can be partial cancellation, but complete cancellation will not take place. So electric field will not be zero even in region 3. So the only possibility left is region 1. Remember students, in such questions it's always better to choose the point. Answer will be, first you decide the region, divide the configuration into 3 regions. Here there is no doubt, here there are possibilities because they are in opposite directions. Out of this, how to choose one? You choose one by deciding that the answer will lie close to that charge which has a smaller magnitude. Here it is q, here it is 2q. Out of these two, which has a smaller magnitude? This one. So your answer will lie close to this point. That's why region 1 will be correct answer. So if this is the correct answer, I will choose this distance. Now from q to 2q, this is given as 1 centimeter. I'll choose this distance which we have to find as r. Then from 2q, what will be the distance? This is r, this is 1. So this will become r plus 1 centimeter. If you wish, you can convert in meters. I am not doing so. It's not necessary in fact here to convert in meters because those factors will cancel. So this point I'll call it as A. The electric field at A is 0. Here the two electric fields are opposite in direction, so they will cancel only if their magnitudes are equal. So E d2 plus 2q charge, its magnitude, and E d2 minus q charge, its magnitude must be equal. Now electric field, what is the formula students? We have discussed 1 by 4 pi epsilon naught. Charge, how much is the charge? 2q divided by square of distance. What is the distance of this point A from charge 2q? So this distance is r plus 1. So we will write r plus 1 whole square, and here it is 1 by 4 pi epsilon naught. Charge is minus q, we are writing its magnitude, so we will write q, and from q what is the distance? The distance is r square. Now here these two factors cancel, q will also cancel. We can take the reciprocal, we will get r plus 1 whole square upon 2 is equal to r square. This 2 will go over to the RHS, 2r square. Now this I can leave, this rest is mathematics. You can solve for this, you will get two values because it is a quadratic equation. So r, you will get two values. Out of them, one might be correct, other one might be wrong. You have to justify that. So just you will get the answer. This is the method for finding the point or locating the point where the net electric field will be 0. The same question if you try to solve over here. Here with the charges that were given were minus q and plus 2q. Here it is minus q and plus q. Such a pair of charges, if this separation is very small, we call it as dipole, electric dipole. Again here, if we ask you, locate the points where electric field is 0. I would request you to give a pause of the video right now, think about the solution in this context, and then after that you resume the video. Okay. Here you will not be able to find any point where the electric field is 0. Any point which is at finite distance from this charge configuration. Reason? Here it's not possible. Reason is same as that question. Here it's possible. Here it's possible. To verify, due to negative charge, the electric field will be in this direction. Due to positive charge, electric field will be in this direction. But this positive charge is separated by larger distance, so its electric field E plus value will be less than E minus, always. Any point you take in this region will always be closer to minus Q, and therefore the minus Q will have greater electric field compared to plus Q. Although their magnitudes are same, but the distance will be always closer for this charge. Just opposite will happen in this region, that is region 3. Beyond this point, whichever point you choose, that will be closer to plus Q, and therefore plus Q electric field, that is this electric field, will be always greater than minus E minus. So here we have the charge configuration like this, minus Q plus Q. So the net electric field in this region, E minus is greater, always will be in this direction, and the net electric field here, E plus, is in that direction, will be in this direction. Here we have this greater, here we have E minus greater. The resulting field will be therefore always in that direction in these two regions. And as we move away and away, the electric field will go on decreasing, and will ultimately become 0 at infinite separation. There is no finite distance at which you can have E is equal to 0 if both the charges are equal. This is not so in this case. These two questions looked very similar, but there is a difference. Here we found, if we are here we got some answer. At this point electric field was 0. What about this point and this point? Before this point, in this region, the point is very close to minus Q charge, so the net electric field will be in this direction. Beyond this point, the net electric field will be in opposite direction. Here this charge will dominate because of its magnitude. It is in opposite direction on either side of this point, and here it is neither in that direction nor in this direction. Here it has 0 electric field, and as you go away and away beyond this point, the electric field will go on decreasing like so, and will again become 0 at infinity, at infinite separation. So this is the difference between these two questions. And one more thing I would like to say, students, combination like this at very far distance, very far, if you go very far, it will behave as a plus Q charge. Plus 2Q, minus Q. Remember additive nature of charges. For points which are very far from this pair, the net charge for this particular point can be taken to be plus Q. So the field here will be proportional to Q by R square, where R is this distance. This will be true only if R is very large compared to this distance between the charges. Likewise, here the pair of charges are minus Q and plus Q. So for distant points very far, this will be almost like a neutral. Here it will not show any sort of electric field. In fact, we will read afterwards that electric field due to electric dipole falls off not as R square but as R cube. It falls very rapidly. Let's see one question. Here we have 4 charges placed at the vertices of a square of each side A, and we have to find the net electric field at the center of the square, that is at point O. We assume all these 4 charges are positive. This charge will have electric field in this direction, and its value will be 1 by 4 pi epsilon naught Q upon this distance square. This is half the diagonal of the square. Diagonal is root 2a. You can find it out. This charge will have electric field in opposite direction like so. This Q charge will also have electric field directed away from it, and this is 2Q. This is Q, so double of this. So the electric field here should be double. So I will draw it by a longer arrow. Remember, in vectors, longer arrow has greater magnitude. So clearly these two if I write it as E, if I write it as E, if I write it as E, this should be 2E. These two electric fields will obviously cancel. Now this is 2E, this is E, so there will be partial cancellation. The net electric field will be E in this direction. So this is E net, and E net will be how much? 2E minus E, that is E. And what will be the value of E? E value we have already discussed, 1 by 4 pi epsilon naught Q upon square of half the diagonal. Diagonal is root 2a, its half is this much. This is the value, and the direction has been indicated by this black line. This is your E net. I'll stop here, students, and I give you 2 questions as homework. These 2 are solved in your textbooks. So these are examples 1.8 and 1.9 from NCERT. We'll continue our discussion on electric field in the next class. So I thank you. We'll meet in the next class.